You're watching a Channel 98 NBISD TV production.
Hello out there in TV land, welcome to Deja Vu, it's Algebra 2. As always, I'm your host, Kevin Corpy, bringing you the math today. Today's lesson 10, we hit double digits finally on this awesome math program, so you've tuned into a winning show. Now today we're going to be talking about matrices, not mattresses, matrices, although some parts might make you sleepy. I'm going to do my best not to let that happen. Log on to the district website, www.newbraunfels.txed.net. Download the worksheets that I've worked so hard to create for you to make it easy for you at home to follow along with me what I'm doing on the show. Grab a sharp pencil, crack your knuckles, and let's get ready to do some math. Matrices today, all right. All right, lesson 10. Today all about determinants and matrix multiplication. Now, every square matrix that we've looked at on previous shows and ones that we're going to be looking at today and ones that you might encounter years and years from now has a unique value that's associated with it. It's a single number that is uniquely associated with each square matrix, and that number is called a determinant with a big D, determinant, although it's a little d. It's a very important word. Now we are going to denote the determinant by using vertical bars, something like this right here. If you've noticed on previous episodes when we talked about matrices, we use brackets to denote the matrix. Well, basically if I get rid of the little hooks at the top of the brackets and I get these vertical bars, I have something that still looks like an ordered arrangement. But this would be what we are going to call the determinant. Now this itself is not a unique value. This is more of like an operational notation that tells us, hey, we need to do something with this to determine that number, called the determinant. Now why do we want to look at this unique number? Well, the determinant can be very, very useful, or quite useful to look at another way. And you're going to see today why that thing is useful, the determinant. So here's the definition of what a determinant is. We're going to go ahead and start with a 2 by 2 matrix. Here's the verbal definition. The determinant of a 2 by 2 matrix is the difference, that's subtraction, of the products, that's multiplication, of the diagonals in the matrix. How are we going to list that numerically? Well, we can write it with the vertical bars, or we can actually take the matrix itself with these little braces and put the letters DET in front of it. That stands for the determinant of this matrix. So both methods are acceptable. Now, how are we going to calculate it? If we look right here, I've actually shown you how we're going to do this. Very important. We're going to take the difference of the products of the diagonals. We must always start with the main diagonal. So if I rewrite the 1, 5, 6, 3 with the vertical bars, 1 and 3, those are on the main diagonal. This plus sign here means that we're going to take that to be a positive number, 1 times 3, down here, 1 times 3, with a positive in front. That's the main diagonal. It has to go first. Now I will subtract. That's what this negative is here. We always subtract right there the product of the other diagonal, 6 times 5. Now because subtraction itself is not commutative, I can't just arbitrarily switch the order of subtraction. So it's very important to start like you would read a book in the top left corner and work along the main diagonal and always subtract the product of the smaller diagonal. And if we do that in this case, 1 times 3 minus 6 times 5 is 3 minus 30, or negative 27. So negative 27 would be the determinant of this 2 by 2 matrix right there without the determinant. We can generalize that now for any 2 by 2 matrix, call it matrix ABCD. The determinant of it, again with the vertical bars, these plus and minuses aren't really part of it, it's just there to help us. It's going to be A times D minus C times B. Okay, and that's going to give us a unique number. So you got it? It's going to be the difference of the diagonals, got to start with the main one first. Now it's very important when we're talking about determinants and we're using the vertical bars not to get it confused with the absolute value. Absolute value is very important, but it's the absolute value of a number. And we looked at that on the geometry show last year. The absolute value of negative 5 is 5. So the symbol that we use actually does kind of look like an absolute value. Let's say I have matrix A. I can write it as the determinant of A, or what looks like the absolute value of A, but it's not. So you have to be very, very aware of the context in which these symbols are written. Because in mathematics, we like to recycle the symbols. And in different contexts, they have different meanings. Okay. Let's go ahead and put it to use. Let's go ahead and find the determinant of this matrix. We'll notice that there's fractions in here, but it's still 2 rows by 2 columns. So this is a 2 by 2 matrix. We can only find the determinant of a square matrix. That's very important. So let's go ahead and do it. The determinant, I'm going to go ahead and write it with the vertical bars. 4, 6, 1/3, and -1/2 equals. So 4 times -1/2, there's the product of the main diagonal. We always subtract in the middle here, and then we take the product of this other diagonal. 6 times 1/3, 6 times 1/3. Now you might be able to do some of that in your head, which is fine. Just be careful as you're writing it down. 4 times -1/2 is -2. Minus 6 divided by 3 is 2. -2 minus 2 is -4. So -4 is the unique value. If we do it right, there's only one we can get for that particular 2 by 2 square matrix. Now, we can step it up a little bit and look at a 3 by 3 square matrix. To do that, it gets a little bit more complicated. It's going to be the same basic procedure, but because there's more numbers, there's more steps. There's 2 methods that we can use. One is called the expansion by minors, which is the one I'm going to show you on today's show, and it's the one probably preferred by your algebra teacher. There's another one that works for diagonal products. Now the reason we're going to do expansion by minors exclusively is because that's a general method that we can extend to 4 by 4s and 5 by 5s. Okay, so I don't have enough space on this page. I'm going to have to do it on another page. Okay, here's our first example. Let's go ahead and find the determinant of A, and we're going to call matrix A some matrix that we don't see. So notice I already have it written in the determinant form with the vertical bars, but it is a 3 row by 3 column. So how are we going to do the determinant? We're going to do expansion by minors. It's typically done by using the first row. Okay, we're going to expand it along the first row. So here's what we're going to do. You can imagine kind of blocking out the first row and first column. Now the number that's on the intersection of the first row and first column is the number 1. That's a very important number. We're going to start with a positive, and we're going to alternate to the next column negative and positive. This number here is important, so here we go. We're going to take that number that's in the intersection of the first row and first column and write it down. 1 times. Now, if we block out that first row and first column, which I'll do with these dry erase markers, notice what we have. We have staring at us a little bitty 2 by 2. Well, we're going to find now the determinant of that 2 by 2. So we'll go 2 times 7 minus 3 times -1. Just like we did for the 2 by 2. So it's going to be 2 times 7, that's 14. We always subtract minus 3 times -1 is -3. Very important, subtracting a negative. So we're done with the first row, first column. Now we're going to go to the first row, second column, and there's a minus. We have to alternate signs. So now we're going to put a minus, always a minus, and we're going to look at that number that's at the intersection of the first row, second column. It happens to be a -2. So we're subtracting, in this case, a negative. And the same thing, we're going to multiply that by, now if we block out that second column and that first row, kind of like a T, notice what we see. We kind of see another 2 by 2 on the edges, a 4, a -1, a 6, and a 7. We're going to calculate the determinant of that. So 4 times 7 is 28. Always subtracting, 6 times -1 is -6. Okay, so now we will proceed one last time. We're going to go along the top row in the last column. That's going to be a 3, and we go back to positive. So plus that number, which is 3, times. And one last time, we will block out the top row and the third column. And notice we're staring at another 2 by 2. So 4 times 3 minus 6 times 2. 4 times 3, the product of that diagonal, minus 6 times 2, which is 12. Okay, so that's the hard part. That's the very meticulous part that requires us to pay very close attention. Positive, negative, positive along the top row. Now all we have to do is go through and do the math. We'll do the inside parentheses first. 14 minus a -3 is really 14 plus 3. So that's going to give us 17. Times 1 is 17. Minus a negative is really plus 2 times. 28 minus -6 is really 28 plus 6, which is 34. Plus, I get 3 times. 12 minus 12 is 0. Wow, it's nice that we get a 0. So after going through and doing all the insides, now I have these little products here, and I'll go ahead and add them up. I get 17 plus 2 times 34 is 68, and 3 times 0 is 0. I'll go ahead and say plus 0. And now it's getting real easy. 17 plus 68 is 85. And that is, in fact, the determinant of this 3 by 3 matrix. So again, the intersection of the first row, first column, that number 1 we put here, and it's positive. And then we multiply that by the determinant of the resulting 2 by 2 that we see. Then we move over and we subtract that number, negative 2, subtract the negative 2, times the intersection of row and columns. So that leaves me with this other matrix right here, okay, on the outskirts. And then we do it for the last one, and we have that there. So you can imagine if we did this for a 4 by 4, how much work it would be, but it's really the same process. It's a systematic routine. Okay? So 85 for a 3 by 3. We're going to stop there today. Okay, so now that we know how to actually find determinants of a 2 by 2 and a 3 by 3, let's put them to use. How are they useful? Well, they're useful in a couple ways that I'm going to show you today. The first way is in solving systems of equations. We've done that on previous shows by using substitution and linear combination or elimination. Well, today we're going to be looking at how determinants help us solve equations by using something called Cramer's rule. Now, if you think Cramer's rule is kind of a law by which actors on sitcoms have to enter a room creatively, you might be right, but in this sense, we're talking about something altogether different. This is a rule that's came about by an 18th century Swiss mathematician, Swiss cheese, I am today, a guy named Gabriel Cramer. He came up with this process using determinants, and it's a pretty nifty way to actually solve systems of linear equations. So here's what we need. We need to be able to write our equations in this format. Our x's first, our y's second, and our constants on the right-hand side. Okay, those are the numbers without variables. And so the a's are going to be the coefficients of the x's, and the b's are the coefficients of the y's. If we write it like this, we can actually create a coefficient matrix by taking the coefficients of x in the first column and the coefficients of y in the second column. That's the coefficient matrix. Okay, it's the numbers in front of the variables. Now we're going to define D, capital D, to be the determinant of that coefficient matrix. Okay, so D is the determinant of the matrix, which is something that we know how to do. In this case, it's a 2 by 2. Now, here's the beauty of it. To figure out what values of x and y in any system make that true, the point of intersection, we can use this little rule. The x solution, the x coordinate of the solution is going to be the determinant of this right here. And all we've done is we've taken our coefficient matrix, and since we're solving for x, we replace the x coefficients with the constants up here, the constants column. And then we evaluate that 2 by 2 determinant, and we divide it by the determinant of the coefficient matrix. To find the y's, we're going to use this formula. We're going to replace the coefficients of y's now with the constants. Okay, so all the b's get replaced with the c's, and we leave the x coefficients alone. If we evaluate that determinant and divide by the determinant of the actual coefficient matrix, we're going to get the solution to y. That's pretty neat. Now notice that if our determinant of the coefficient matrix is 0, it's going to be undefined because we're dividing by 0. Let's go ahead and give that a try. We're going to use Cramer's rule to solve this system of equations. The first thing we need to do is make sure it's written correctly. I need my x's and y's and my constants on one side. So this becomes 2x plus y equals 10. You got to be careful just because something's handed to you. It might not be in the best form that we need to use it in. So a quick check and a quick rewrite, and now we have our x's and then our y's equaling our constants. So let's go ahead and create the coefficient matrix. The coefficient matrix, I'm going to go ahead and calculate that off to the side so I can refer to it instead of having to calculate it each time. It's going to be 2, 3, the coefficient of the x's in the first column, and then 1, negative 2. So there's the coefficient matrix. Now I'm going to go ahead and calculate the determinant of that. So that's just a rewrite without the brackets, and it's a 2 by 2. So remember, it's 2 times negative 2. That's negative 4 minus 3 times 1 is 3. So that's negative 7. And that's my D in the formula. That's the coefficient of the determinant of the coefficient matrix. Now, let's go ahead and apply the rule. The x coordinate is going to be the determinant of, since I'm trying to solve for x, I'll replace in the coefficient matrix the 2 and the 3 with the constants. Now our constants are right here, 10 and 8. And I replace the x's because that's what I'm trying to solve for. So I have a 10 and an 8. And then I'm going to leave the y's the same, 1 and negative 2. And I will evaluate that and I'll divide it by d, which is negative 7. So let's see what that comes out to be. 10 times negative 2 is negative 20, minus 8 times 1 is 8, all over negative 7. And now we get negative 28 over negative 7, which is 4. So that's the x-coordinate that makes this solution true, or the x-coordinate of the point of intersection of those two lines. Pretty cool. Doing it for y, it's a very similar process. We just replace the y coefficients, or the second column, with 10 and 8, the constants, or the solution column. So I get 2, 3, the x's go along for the ride, and now the 1 and negative 2 get replaced by the 10 and 8, and then I'll divide that by the determinant, which is negative 7. And then we'll just proceed. Evaluating the numerator, I get 8 times 2, which is 16, minus 30, all over negative 7. And that's going to give me negative 14 over negative 7, which is positive 2. So that means the solution to the system of equation is the ordered pair xy, which happens to be 4, 2. It's a very systematic process that works equally well for systems in 3 variables, 4 variables, but again, it's just going to involve more steps. So Kramer's rule. Might seem a little bit uncomfortable now, but it's really a systematic, easy process that once you understand how to do it once, you do many problems and you just get better at it. All right, let's take a real quick break, watch some very valuable public service announcements. But while you're gone, think about this. What do you get when you divide the circumference of a pumpkin by its diameter? Huh? The answer when you get back.
My cell phone number.
The odds of a babysitter calling 911, 1 in 1,400. The odds of a child being diagnosed with autism, 1 in 150. To learn the signs of autism, go to autismspeaks.org.
Welcome back to Deja Vu, it's Algebra 2. I'm your host, Kevin Corpy, today talking to you about matrices, the wonderful world of matrices and determinants, right? Now, when you were gone, I hope you were thinking about what you get when you divide a pumpkin's circumference by its diameter, huh? The answer, pumpkin pie. Back to the math. All right, so how else are determinants useful? Well, we can actually use determinants not only in Kramer's rule to solve systems of equations, but we can use them to find multiplicative inverses of square matrices. Okay? Now remember that a multiplicative inverse of a matrix, or we just call it the inverse matrix, is a matrix that we need to multiply by to get the identity matrix. Okay? So if we have matrix A, first of all, we're going to denote its inverse again by writing it as A to the negative first power, essentially. So we read that as A times A inverse. That should give us the identity element for matrix multiplication. And remember, matrix multiplication in general is not commutative, but when I'm multiplying two matrices together and their inverses, it should be. And they should both give me the identity. Now remember, here's what an identity is. An identity matrix element for a square matrix has 1s along the diagonal and 0s everywhere else. Not 1s everywhere, just along the diagonal, 0s everywhere else. So, here's the definition of an inverse of a 2 by 2 matrix and how it involves the determinant. Let's say we have matrix A, it's A, B, C, D in this arrangement. Here's what we're going to call the inverse then. First of all, the notation is A inverse, A to the negative first, equals 1 over the determinant of A. There's the determinant showing up. The reciprocal of the determinant times this matrix. Ooh. Well, notice how it's related to the original matrix. Our original diagonal, AD, is now interchanged, DA. We have to switch the elements or the entries on the main diagonal. The other diagonal, CB, they stay put, but now they become the opposite sign. So again, 1 over the determinant times the matrix that we get by switching the members along the main diagonal and taking the opposite of the elements or the entries on the other diagonal. Now what if the determinant is 0? If the determinant is 0, 1 divided by 0 is undefined. So we would say that the matrix does not have an inverse, or we call it a singular matrix. Okay, so here we go. We want to find the inverse of this 2 by 2 square matrix. We're going to call it matrix M. And once we find the inverse, we want to verify that it is by multiplying m, this matrix, by the one that we find. Remember, we should get the identity element. 1's on the diagonal, 0's everywhere else. So the first thing I'm going to do is I'm going to actually find the determinant of m. So we write that 4, 2, 3, 1. And then we do what we did previously. 4 times 1 is 4, minus 2 times 3 is 6. So I get negative 2. So there's the determinant. So the inverse matrix, m inverse, will be 1 over negative 2, or negative 1/2, times the matrix 4 and 1 switch. So I have to switch the main diagonal. So instead of 4, 1, I have 1, 4. And then the 2 and 3, they get their signs changed. Negative 2, negative 3. It's important that we switch the matrix. I almost did not do that out of reflex. I was rewriting it. 4, 1 becomes 1, 4. 2, 3 becomes negative 2, negative 3. Now, this is scalar multiplication. I'm multiplying a matrix by a scalar quantity. So remember how we do that? We have to distribute this negative 1/2 to each of the 4 entries. So that's going to give me negative 1/2. Negative 2 divided by negative 2 is 1. Negative 3 divided by negative 2 is 3/2. And 4 divided by negative 2 is negative 2. So that should be the inverse matrix right there. Okay? Now, how can we verify that? Let's go ahead and do m times m inverse. What's it going to be? It's going to be 4, 2, 3, 1, the original matrix, times this new one that I found, negative 1/2, 1, 3/2, and negative 2. Now again, when does matrix multiplication work? Well, this is a 2 by 2, or multiplied by a 2 by 2. So when these numbers are the same, it'll work. And we're going to result in an outside matrix, which is the 2 by 2. So let's go ahead and see what we get. Remember how we do this. We're going to go along the first row and the first column. We're going to multiply and add the product. So 4 times negative 1/2 is going to be negative 2, plus 3 times 1 is 3. So that's my new 1, 1 position. Top row, second column, gives me my new 1, 2 position. So 4 times 3/2 is going to be 2 times 3 is 6. And then I'm going to go 3 times negative 2 is minus 6. Then I move down to the second row, first column. 2 times negative 1/2 is negative 1. 1 times 1 is positive 1. That's my new 2, 1 position. And then finally, second row, second column. 2 times 3/2 is 3. And then finally, 1 times negative 2 is negative 2. And I just have to simplify that. 3 minus 2 is 1. 6 minus 6 is 0. Negative 1 plus 1 is 0. And 3 minus 2 is 1. Looky there. I got the identity matrix. Now, we don't have time, but you could verify at home that if you do m inverse times m, you actually commute it, you should get the same thing. So commutative matrix multiplication only works when they're inverses or one of them is the identity. In general, it doesn't work, though. Now it's the time in the show where we like to do something called
Deja Review.
Okay, so what we're going to do now is we're going to come with a very, very, very powerful method for solving systems of equations. And it's going to emerge when we combine the two things we learned about matrices, matrix multiplication and inverse matrices. Now, the calculations can become very, very tedious, mechanical, and systematic. So we're going to let our calculators do it for us. Now, here's what we're going to do. We're going to try and solve this 3 by 3 system of linear equations. Like we did on a previous show, we did it by double elimination. It took a while. Well, watch how easy this is going to be. The first thing we want to do is write it in our standard form. So we're going to have to rewrite it. And I'm going to have x, y, and z. So I have 5x plus 7y minus 3z equaling 3. Second one, 3x plus 4y plus 2z equaling 6. And then finally down here, x plus 3y minus 5z equals negative 7. So what I'm going to do is I'm going to create 3 matrices here. I'm going to create matrix A, which is going to be my coefficient matrix. And then I'm going to create a variable matrix, which I'm going to call x, variable matrix. And that's going to equal what I'm going to call B. And that's going to be my constant matrix. Okay, so it's kind of the way I have it written here. So here we go. Matrix A is the coefficient. So the way I have it written, x's, y's, and z's. So it's going to be a 5, 3, 1. The first column is my x coefficients. And then I'm going to have a 7, 4, 3. Those are the coefficients of y. And then I'm going to have a negative 3, 2, negative 5. Those are the coefficients of z. So that's matrix A. Now matrix B is going to be my variables, x, y, z. And I'm going to write it like this, as a 3 by 1. Because a 3 by 3 times a 3 by 1 should work, since these are the same, and I should get a 3 by 1 as my result. Well, guess what that 3 by 1 is going to be? It's going to be these constants right here, 3, 6, negative 7. All right. Now, I've kind of made this problem look a lot more uniform. But how do I use it? Well, oops, I called this b. It should be x. My bad. This is b. I have ax times b. Here's what I'm going to do. I'm going to do a little bit of algebra over here with matrices symbolically. I have ax equals b. What I'm going to try and do is solve for x, the variable matrix. And how do I do that? Well, I have to multiply both sides on the left by the inverse of a. So a inverse times ax equals a inverse times b. And I have to do it on the left-hand side because that's where this a is. There's only room on the left. And I have to do it on the left on this side since matrix multiplication is not commutative. Now, what is a inverse times a? Well, a inverse times a is the identity matrix. So I get the identity matrix times x is a inverse b. Well, what's the beauty of the identity matrix? The identity matrix times anything is just that thing itself. So I get x, my variable matrix, is equal to a inverse b. And that's something that our calculator can do. Now for us, finding the inverse of a 3 by 3 is not very fun. It's not very easy. So we're going to let the calculator do it anyway. So once I get my matrix A into my calculator and my matrix B into my calculator, all I have to do is let it perform this little operation for me, and my solutions, x, y, z, will magically appear. Let me show you how to do that. Okay, remember how to enter data into your matrices. You're going to go to second matrix, and we're going to edit them. I already have the information inputted in here because it just takes a while, but you're going to pick edit and type in the dimensions and carefully type in your data. So again, we're going to type in the coefficient matrix into A, which is a 3 by 3, and the constants on the right-hand side of the equation in matrix B, which is a 3 by 1. Then we're going to go back to our home screen, and from there, all we have to do is recall the two names. So second matrix, we're going to recall matrix A, and watch this. Finding the inverse of a 3 by 3 by hand is very, very unfriendly. But if I just hit A inverse, right above the x squared, there's an inverse button. It'll actually give it to me. Now, it's not a very nice decimal, but I don't even have to know what that is, because if I just recall A inverse, which is really what I want, and I take that and I multiply it by matrix B. So A inverse, just recall matrix name B. Writing them side by side without a multiplication is acceptable multiplication. That's what I want. Now watch this. When I hit enter, look what happens. I get a 3 by 1 generated, and it tells me that the x is 4, the y is negative 2, and the z is 1. So this is essentially what the calculator is telling us. X is 4, y is negative 2, z is 1. So the solution, x, y, z, if you want to write it as an ordered triple, is 4, negative 2, 1. And boy, that whole A inverse B trick is very nice now that we know how to do it. Very nice. Hope you enjoyed that great show today. As you can see, matrices are very, very useful, very, very important. The thing is that the calculator can do the little operations that are kind of tedious for us to do by hand. Because it's an ordered arrangement, we can systematically tell computer programs what to do, which is very nice for us because we can free up our mental processor for other things like more math problems. Yeah, and we're going to do that as the year goes on. So I hope you enjoyed today's show. That's all we have time for today. Even though I'm not wearing my watch, I know it. I have one up here. Till next time, I'm Kevin Corpy, reminding you to do your homework.